Greetings, ladies and gents, and welcome back at Semi Math and Science Club. In the previous video, we looked at the first extended practice question, which was this question that we covered. So in this video, we'll be looking at the second one. Now remember that of course this extended practice questions are actually dedicated on that second video, that lesson 2, which was in this case based on the energy part. So in this case, the first video that we did was in this case on work done. The second one was in this case on energy. So in this case, this videos. So this is actually the second one. So in this case, this extended practice questions, they actually in this case dedicated to that second video, that energy video that we did. So if you haven't watched that, I would strongly suggest that you go and watch that before you watch this video here. So what I'm simply going to do, I'm also going to leave in this case a link to that video there, so that you can refer back and come back to this one after you have watched it, the first one. So in this case, for question now, by the end of this video, if you feel like of course it helped you at some extent, be sure to leave a like. And also, if you've got any question that you would like to ask, you are more than welcome to throw that in the comment section. Right? Or if you've got any topic that you'd like me to cover, you're more than welcome. Just throw that in the comment section, whether being in maths or physics. So they said that for question 2, the diagram below shows a track ABC, the curved section. Again, I come with that pronunciation there, curved. Yeah, I don't understand my English. I don't understand it. So they said that of course that section there, the curved one, AB is frictionless. All right, this section here, it is frictionless. Right, so they are telling us that in this case we do not have friction between point A and B. So they said that the rough horizontal section BC is 8 meter long. So in this case, between this point, we actually have in this case we have the frictional force. So in this case, between these points, so in this case we are actually kind of in an isolated system. Why? Because only between point A and B. Why? Because in this case we do not have the upright force there, we do not have the frictional force or tension or any other external forces there. So in this case we can actually use the mechanical energy if we want for that section B, for that section AB. But in this case for BC we cannot. Why? Because we have external forces. The external forces, which is in this case the frictional forces, they say that's a rough surface there. Right, so if we continue with our statement, they say that an object of mass 10 kg is released from rest. Is released right from point A, which is 8 meters above the ground. It slides down the track and comes to rest at point C. So in this case, that statement there, released, it simply tells us that in this case the speed of the object at that point A is 0. Right, and then they also tell us that the speed of the object there at point C is simply 0 by that statement there, which is, they say that it comes to rest at point C. So for 2.1, they say that state the principle of conservation of mechanical energy in words. So we know that, of course, the principle of mechanical energy in words simply states that in this case, in an isolated system, the sum of the kinetic energy and potential energy is conserved. Right? So in this case, that's the formal definition of mechanical energy, of the principle of conservation of mechanical energy. It says that in this case, in an isolated system, the sum of the kinetic energy and potential energy is conserved. Or you can say that in this case so you can also say that in this case, in an isolated system, the mechanical energy is conserved. Right, so for 2.2, they say that is the mechanical energy conserved as the object slides from A to C, and we know that of course the answer for that is simply a no. All right, and the reason for that is because remember that in this case we can only say that the mechanical energy is conserved between point A and B, but in this case on this entire section we cannot say that in this case the mechanical energy is conserved there. Why? Because in this case between point B and C we have non-conservative force, which is actually the frictional force. So in this case for 2.3, they say that using energy principles only, calculate the magnitude of the frictional force exerted on the object as it slides along BC. Now remember that these are the energy principles that we have, right? So in this case, so they're saying that you must use these energy principles. Now, for us to calculate the magnitude of the frictional force, so in this case, what you would need to do would be in this case to either use this one or that one only on that section, as in this case, because we know that of course between section BC, this is where we have in this case our frictional force. In this case, we can either use this one or that one. It really does not matter actually. So in this case, for us to use any of these equations on that section there, we would actually need to know the speed of the object at that point B there, because in this case you notice that in this case these equations include both the speed of the object at this point and at that point there. We do not know the speed of the object at point B. So in this case, what we are simply going to do would be to first calculate the speed of the object at point B. Right, so in this case, we know that of course it was released from rest, and in this case we want the speed of the object at point B. So in this case, what we are simply going to do would be to use the mechanical energy between point A and B. Why? Because in this case we do not have friction there. So they say that that's actually a frictionless surface there, or section. So in this case, what we are simply going to do would be to say that the mechanical energy at point A will simply be equal to the mechanical energy of the object at point B. As in this case, what we can expand this to be mgh at point A plus in this case a half multiplied by the what we have there, multiplied by in this case by the speed squared at point A. So this will be equal to the in this case to mgh at point B, and this is plus in this is half mv squared at point B there. So in this case is the potential energy or the mechanical energy of the object before, this case equal to the mechanical energy of the object in this case after. So in this case we can say that in this case, so the mass of the object, that's 10, multiply that by 9.8, multiply by the vertical height when this object was at A, which is actually 4. So it's multiplied by 4. And we, in this case, what we now do would be to say that plus a half multiplied by 10 multiplied by the speed. They say that that object started from rest, so that would simply be 0 squared equal, so it's the mass, which is 10 multiplied by 9.8 multiplied that. So in this case, we know that of course when that object is at point B, it is actually on the ground, right? So in this case we can say, so we say that in this case, so when the object is on the ground, so the vertical height will simply be 0. So in this case it will be plus a half multiplied by, in this case, by the mass, which is 10 multiplied by VB squared there. So in this case you notice that these two, all right, are simply going to give us a bunch of zeros. So in this case, what we would actually be left with is simply these two. So in this case, what you're simply going to do, if you put this into your calculator, what you're simply going to get is actually, if you put this, what you're going to get is actually 392 being equal. If you put, now remember that a half multiplied by 10, you're actually going to get 5 b squared. So what you're going to do would be to divide by 5 on both sides. So if you divide by 5 on both sides, what you're actually going to get would be 78.4 being equals to v b squared. Take the square root, and in this case your answer for the velocity at point B would simply be equal to, in this case, 8.85. That's 8.5 there. So in this case, meters per second, if you round that off. All right, yeah, you can leave it like that. Now again, remember, this is actually a rounded version of the answer. So in this case, remember that we are not in this case on the final answer. So in this case, what I'm simply going to do, in this case, let me just drag this a little bit so that in this case you can, right, so in this case we have 78.4 there. So in this case, what I'm simply going to do would be to say 78.4 being equal to, in this case, to v b squared. So take the square root on that point. This will simply be, in this case, vb equals to, in this case, if I round that off, simply be 8.85 meters per second. But remember, we can't round off our answer. Why? Because in this case we are not at the final answer yet. So in this case, where there is actually, now I'm gonna show you something a little bit how we can actually avoid using that one there. So in this case, what we are going to do now, so now we know that of course the speed of the object at point B is 8.85, is approximately to that. So in this case, what we can now do would be to use any equation that we like between these two to calculate, in this case, the magnitude of the frictional force. So in this case, what I'm simply going to do would be to use this one. Now this one can also work, all right, but in this case this will simply be 0. Why? Because in this case, as our object is traveling between these 2 points, we do not have, so in this case our object is not elevated any units above that horizontal section there. But in this case, to make things easy, I'm simply going to use this one, which says in this case W net simply be equal to the object's change in to the change in the object's kinetic energy. So simply be in this case to W net. Now remember that this object is sliding between point in this case BC. So in this case we actually have, in this case, our frictional force. We have in this case our Fg. We also have in this case our normal force there. So in this case we do not have actually an applied force. So in this case, what we are simply going to do there would be to say that F net will simply, W net will simply be in this case work done by, in this case, by Fg, plus work done by the normal force, plus in this case work done by, in this case, by Fk, by the frictional force. Right, so that's actually work done by in this case by Fk, which simply be equal to the change in the object's kinetic energy. So in this case, remember that these two, they're actually perpendicular to the surface, so they're actually going to give us, in this case, a bunch of zeros. So in this case, what will simply be left with will simply be that work done by the kinetic friction. So in this case, simply be equal, so simply be in this case Fk multiplied by the displacement multiplied by the cos of theta. Right, we are now calculating the work done by that. So in this case, so it simply be equal to, in this case, to the half mass multiplied by the speed squared at point final, right, at point C, minus, in this case, a half multiplied by the mass multiplied by the speed at point B, square that. So in this case, what we now have would be, so in this case, what we can now do would be to substitute our values. So in this case, we are looking for Fk multiplied, we know that of course the displacement, that's actually 8, simply be 8 multiplied by the cos, right? But in this case, our theta, remember that in this case that theta there is simply the angle between the direction of the displacement, in this case, and the direction of the frictional force. So in this case, we know that in this case our frictional force is in that direction. In this case, our displacement is in that direction there. So in this case, the angle between them would simply be, in this case, 180 degrees. So this would be cos of 180 degrees. So in this case, let me just erase this. So in this case, what we now have would be equal to, in this case, a half multiplied by mass, which is, I think that was a, let me just go, that was a 10, multiplied by the velocity at by the speed of the object at point C. They said that it stopped when it reached the point C. So it will be 0 squared minus a half multiplied by the mass, which is 10, multiplied by the velocity at point B, which Vp squared. Say that, now remember that Vp squared is actually 78.4. So I'm actually going to multiply this by 78.4. Right? Let me just use that the one that which is not rounded, since this is not our final answer. So in this case, if you put cos of 108, you're actually going to get a -1. So this actually turned to -8 multiplied by Fk, being equal to, in this case, if you put this into a calculator, what you're simply going to get is actually -392. So in this case, you divide by -8 on both sides. What you're simply going to get is Fk simply be equal to, in this case, 49 Newton. So in this case, this will simply be the end for this video, for the second video. Again, there's another one to follow. So this is the third one. So be sure to of course watch out for that. So again, if this video helped you at some extent, be sure to leave a like. If you haven't subscribed, be sure to hit that subscribe button and also that notification bell, so that when the new videos comes up, you'll be the first to be notified. But otherwise, as the story always ends, ladies and gentlemen,